Shall I share a screen? You would, Mayank?
Yep, yeah, please do.
Okay. Yes, so today we start a new part of the book, which is approximate solution methods. And as a initial kind of motivation here is very simple. So far we considered tabular methods, which are kind of well studied and well understood theoretically, has a nice kind of convergence properties with solid proofs and all, but for almost any kind of practical problem, we cannot have all states assigned kind of separate memory location as we do in tabular methods. And furthermore, in many practical problems, we don't have any notion of separate, like discrete states. So the state may be continuous, right? So therefore, we need to move from exact tabular methods to approximate methods. And another important property of approximate methods that we expect to have some generalization. So when we use appropriate functions for approximating the value, we expect it to generalize in a sense that we can get meaningful interpolations between the observed data points. And in the best case scenario, I guess we have interpolation or extrapolation to some unseen states. And obviously this wouldn't work with tabular methods when we have like each state is associated with a separate entry. So instead of representing our value function as a table, we can represent it as an actual function, which is parameterized by some weight vector W here. And yeah, actually, this does not have to be a vector. It means just we have some like parameterized function. And this function takes in some, so here you can see that v hat is a function of state and W, and it should be approximately equal to the actual true value function for a given policy by. Okay, so and that is what we will talk about in this part of the book, and in particularly in this chapter 9, we will focus on policy prediction using approximate methods. So we don't talk about controls. We follow the same kind of pattern as before. We first consider the prediction problem, and then we will talk about the control problem afterwards. Okay. So here we have so our weight vector is in RD, where D is some integer value, so the number of parameters we have, and it is usually assumed to be much smaller than number of states we can have. So here you can see that the state space size is much larger than number of parameters we have. And therefore, we need this value function to generalize, to produce some meaningful results. And as I mentioned before, the generalization makes the learning potentially more powerful, yeah, but also potentially more difficult to manage and understand. So that's an important point about function approximation. Yeah, and we will see that the extension of the methods we discussed so far to the function approximation approach will be not as like complicated as one could expect. So most of the methods definitely need some changes, but also have a lot of similarity with what we discussed before with respect to tabular methods. Okay, so here we talk about probably everyone here is well familiar with deep learning and machine learning in general, and like the idea of function approximation is not new to everyone here. So in some sense, this will be kind of recap of the very basics of something we are probably all familiar with. But on the other hand, we will have this reinforcement learning flavor of it, and we will see how some implications of function approximation project to the reinforcement learning problem formulation. Okay, so let's have a look at the prediction objective we have under function approximation task. And here's this VE bar of W is our prediction objective, and it is just the squared difference between true value function. So this component here, V sub pi of S, is our true value function, and V hat of S and W is our approximate value function. And also we have this mu here, which represents the state distribution. And as any distribution, it should sum to 1. So it represents, so here it's kind of very general. So it represents how much we care about the error in each state S. Okay, so to summarize, in this formula, you see that our total objective is a weighted sum over all states of square differences between true value function and approximate one. Okay, so that's just yeah. If you think about it, that just we try to learn some value function. So this is kind of almost a regular weighted regression objective, right? And in this case, we just do the regression of a value function. Okay, so that is not new to those familiar with machine learning in general. Yeah, and here a bit of details. What is a state distribution, and here we have a kind of write up what does the state distribution for like on policy distribution in episodic task would be. Yeah, and here basically you can see that it is how many times do we end up being in some state S, and the distribution is just a normalized value for each state. How many times do we this state is encountered, right? So and here you can see that this can be also combined with some discounting factor, and it would be incorporated in this part of the equation. Okay. Yeah, and here, as always in optimization problem, like in in best case, we hope to find a global optimum, but it is not always the case that we are guaranteed to find a global optimum. In particular, like many gradient descent algorithms are guaranteed to find global optimum only for strictly convex functions or concave, right? Depending on if we are doing minimization or maximization. And in more general case, we converge to local optimum, and the hopes are that the local optimum is good enough to, you know, to work, right? So yeah, and also we converge not exactly to the optimum generally, but rather we would converge to be close enough to like close to the point which is close enough to the global or local optimum. Yeah, so that is our problem setting. I'm just you know, going in through it quite fast, and feel free to jump in to do any additions or ask any question, because I believe this is very familiar to everyone, because it's kind of the very basics of you know, machine learning and optimization. Yeah, so here we will encounter one thing which arises from the fact we are doing reinforcement learning. This is a semi-gradient methods, and yeah, it's not particularly because of reinforcement learning, but because of bootstrapping. So let's get to that. That's quite interesting, I guess. So here we have some, again, weight vector, which is W1 to WD, so a bunch of coefficients. And in the very simplest case, which is a linear case, it will be just a single vector, which will be multiplied by a feature vector, which is of the same size as W. So in this chapter, we will be mostly talking about the simplest linear case, because it's well studied and understood. But again, everyone here is familiar with deep neural networks and how they work, and the ideas are mostly extensible to that directly. So the stochastic gradient descent, right? Here we try to find the W t plus 1 as W sub t minus 1/2 of alpha, which is our learning rate or step size for the gradient descent. I just, we usually call it learning rate in machine learning, but in optimization in general, this is just a step size for the gradient descent, right? And here we have the gradient of our objective function. And you see that the objective here is squared difference of true value function and the approximated one. And you can rewrite it using the chain rule, right? So we get a gradient of a squared function. We can rewrite it like this. So the equation 9.5, it's just a gradient of mean squared error or squared error objective here. And you can see that so important thing to notice here, that we assume that our, and yeah, it's obviously the case here, that our true value function is independent of our weights, right? So that is why it is treated here as a constant. So it's independent of W, but when doing bootstrapping, it will be more tricky. So we will get to that. Okay, so yeah, the true value function is generally not known to us, obviously. And that's why we are trying to approximate it in the first place, right? So here we can denote our, so this makes this equation here kind of useless, because we don't have a value here, this value v sub pi of st. But we will define some update objective denoted here as u sub t, and it will be dependent on the reinforcement learning algorithm we use, what the update objective would be. Okay, so we rewrite the update equation using this newly introduced update objective, and it becomes like this. And if the update objective is unbiased estimate of the true value function, then W sub t is guaranteed to converge to local optimum. So yeah, for decreasing alpha, that is just from general stochastic gradient descent properties. Yeah, that is well studied and proved for in classic optimization. Okay, so
Here,
now let's
U of t is the unbiased estimate.
yeah, if U of t is unbiased estimate, we will converge. The convergence is guaranteed. So it not always the case that U sub t is unbiased estimate, and we will see it that it's not the case for the TD methods, and that will So I think this is in this part. So we are just getting to that. So it is unbiased estimate for the Monte Carlo approach. So the Monte Carlo algorithm, we have like a complete episode. So so here we use expected returns G sub t as our update goal, right? And in Monte Carlo algorithm, the expected returns are unbiased because we just sample them independently, and therefore, yeah, like we just have a bunch of independent samples of expected returns for each episode, and the expectation would be an unbiased estimate of true value function. And yeah, so this here is our update for the weights of our function under Monte Carlo algorithm for estimation. So yeah, that something new, but also I think it should be familiar and very similar to the Monte Carlo update for tabular method, right? We just move towards the using the difference of expected return and our current estimate of the value function. But in this case, we don't we do not change the particular value associated with some state S sub t, but instead we update the weights of a function based on the observation made in this state. All right, and now let's move to the algorithms that are used in bootstrapping. So why is bootstrapping here is a bit different? Because in a bootstrapping, so the whole idea of bootstrapping is to use the learned values of value function to estimate the expected to approximate the expected returns, right? And the problem here is in the fact that our value for the expected returns becomes dependent on W itself, right? So we kind of bootstrap the value based on its so we are trying to use bootstrapping based on the same W here, right? And in this case, we are not the convergence is not guaranteed, so that's a problem for gradient-based algorithms. So let's have a look at how this can be kind of solved. So instead of using true gradient method, we will be using semi-gradient methods. So the semi-gradient methods I believe is kind of, we do not. So here you can see that our kind of, yeah. So in the first place, when doing this derivation, so the u of u sub t here was obtained by assuming that like we first took advantage of the fact that true value function is independent of w, and therefore we can find a like gradient, like applying the chain rule, we rewritten the gradient of this the objective, right? And then turns out that our update target here is dependent on the w, okay, because we are trying to bootstrap. So, and in this case we change algorithm as follows. So it will not be an instance of true gradient descent, so it will be like a semi-gradient method, right? Because this value here wasn't originally kind of dependent on w, but we are going like we compute the gradient with respect to the value for state s, but not to for the value of state s prime, right? So that is my understanding. Is it okay with everyone?
Yes.
Okay, cool. So and here we will just try to work through a simple example. So state aggregation, it's the simplest or one of the simplest form of generalizing function approximation. And in this case, we will just group states together into some predefined number of groups, and we will use a single value for each group instead of having a value for each state. And the value of a group will be just an average of the values of states in the group. And we can, again, we consider the random walk example, which we first discussed in chapter 6.2. So what we have just our Markov process with 1000 states, and we randomly transition with equal probability to the left and to the right within a boundary of 100 states in both directions, I guess, or yeah. And when we hit the boundary, so in the leftmost and rightmost states are terminal states, and when we transition to those states, we get a reward. And in this case, we have a reward of 1 in the rightmost state, terminal state, and in the left terminal state, we have a reward of -1. Okay, and here you can see the true value function v sub pi shown as a red line, and you can see that we are trying to approximate this red line by kind of, you see this stepwise, so piecewise approximation this stepwise function here is our approximation to it. Okay, and we have notice that we have a state distribution here, so the states are not equally likely. We have this spike here in the initial state, which is right in the middle, and then we have this kind of less and less probable being towards the end. And that is why our approximate function here is biased, and you can see that it deviates more like towards the higher values here and lower values towards the end, because we have more. So the further we get to the right terminal state, the higher true value function is for that state, and the closer we get to the left terminal state, the lower the function is. But you can see that the most like the states closer to the boundaries are less probable, and therefore they have less weight in our approximate function. And that's why you can see that these steps here, they are not centered kind of with respect to the line. They are somewhat shifted, and it's most obvious close to the boundaries. All right, so that is our kind of learned function, and yeah, one can learn it. So this example is learned with gradient descent, and it took okay 100,000 episodes to approximate that, to get this results with yeah, and that was done with Monte Carlo algorithm. Okay. So any comments on this example? Okay, cool. Now, so we considered this state aggregation, which is very simple, but also, yeah, obviously it's not very accurate. And yeah, it's, you see that we have only one value for a bunch of states. So how can we do better? And first simple way to improve it would be use linear approximation. So in this case, our value function will be approximated as a product. It's or dot product of two vectors as a weight vector W and feature vector x, which is x of s. So our state is encoded as some feature vector, and yeah, and then we just took a linear combination of those features, and so here we have a very important question, and that is kind of behind most of the classic machine learning. How do we design a good feature vector? And here in the coming chapter, we will consider a bunch of methods. How can you construct some features from the state? And in general, this the best choice would be dependent on the particular problem we are dealing with. And yeah, so it will probably rely on our knowledge of the environment to construct good features. Okay, and the stochastic gradient descent update is particularly simple in this case because the gradient of value function would be just x of s, right? So we have a linear function, and the gradient of linear function is just the kind of coefficients. And here we compute a gradient with respect to w, so the coefficients are x's, and so that is our gradient, and our update becomes of this form. Okay, now we can consider the semi-gradient TD update for this. So this is a general formula, right? And we need to substitute some update target for here. And in case of TD0 algorithm, the update target is our observed reward plus discounted value of the next state minus the value of this of state s sub t, right? So, and here x sub t plus 1 and x sub t would be the feature vectors for the corresponding states, s sub t and s sub t plus 1, right? And after doing some rewriting, we can express the update for this is again, this is particular for the linear case, and here you can see that it is rewritten in this form when we have some constant vector, or this vector is independent of w, so that depends on the reward and the features. And here we have some matrix multiplied by our weight vector, and this matrix is a how it's called, I don't know, get a cross product of these two vectors, right? X t and x sub t minus gamma x t plus 1 transposed. So that is,
I think it's the outer product.
yeah.
Yeah.
Correct. I just forgotten how it's called. Correct. Thank you. Yeah. So the outer product of two vectors would be a matrix, and that would be our matrix A here. Okay, and that would be the expected update, right? So or expected value of the next, so the value of the weight vector for t plus 1 given a weight vector for at times t. Okay, so and here we can solve this. So the gradient descent converges when the gradient is 0, right? And for the linear case, we can solve it to find the fixed point. So that would be a value to which the semi-gradient TD should converge. So that would be the fixed point of linear TD0. And yeah, so there is a proof of convergence for this for this gradient descent algorithm, but I think we can skip the details here safely. And also it is convergent to the, and there is an error to which it converges is upper bounded by this value, where so this would be like minimal error we can get using Monte Carlo method. So that would be so Monte Carlo method is unbiased, and the minimal error we can get with a Monte Carlo method multiplied by this value, which depends on gamma, so the discounting factor, that will be upper bound for the error to which the TD0 will converge. And so gamma is usually chosen to be close to 1, right? And therefore, the upper bound may be quite high for this TD method, but well, it's also said that in practice, it usually works well. And again, the authors in the book mentioned that yeah, usually the TD method converges faster. So all the same benefits we had for temporal difference learning for tabular methods are still applicable here. Yeah, but that comes in cost of this increased, at least like the upper bound for the error we can get is potentially much higher. Okay. And here that it is stated that also similar bounds are relevant to other bootstrapping methods. So for example, dynamic programming is bootstrapping, right? And there are some it is also related to can be related to the Monte Carlo with some bounds, the error associated with the method. So here we can see the results of running bootstrapping algorithm on the same problem we saw before. And you can see that the results are much worse, right? So the error here will be quite a bit higher compared to the Monte Carlo method we saw before. And here you can see also the comparison of the resulting error and as a plotted the dependence of the resulting error on the learning rate and number of bootstrapping steps. So you can see the curves here, and for this particular problem, you see that number of bootstrapping steps equal to 4 works best. So that's kind of interesting, right? We have here this curves are very similar to what we saw earlier in the book, and those similar curves were produced for, I believe, like 6 state, or no, like 20 state or something like that, right? And here you can see that we have some number of this aggregates, and maybe this choice of n would also depend on like how many aggregates we have in the function. So that would be something interesting to experiment with.
Yep.
Okay.
Let me try to share the figure that I had. I made that using.
Yeah. So I'll stop sharing.
I hope you can see this.
Yep.
So yeah, this is the steps that we can see. So there's a bit of a difference between how they have presented it here. This is how it forms here. You can notice in the middle, the vertical spaces near the center of the red line, it gets reduced. It's because the value at the scale, it's kind of like approaching the value is approaching some sort of a equilibrium near the middle of the state. So as they have divided it into, I think so it's 20 groups of 50 state each. So uh, on the 100 states. So here, these are the 100 states. So this value is constant here. For each of the 100 states, some values are constant, and the two values kind of like uh, the the approximate TD values versus the true TD values. They try to uh, go up and down. Yeah, you can see here. These are the true values. These are the approximate values here. Sorry, this is the true value. The red line is the true value that it gives. Yeah, you can see this approximately the value of the p hat that we try to achieve. This was a bit of a difference, and since this is like 0.4 and it has the lowest here, so yeah, n is equals to 4 is the best possible solution that we have here.
Can you run it with a different number of aggregates? I mean, say, change it to be 20 instead of 10.
Then those aggregates are taken. Those are must be only give from 1 to 1,000. Those aggregates.
And it seems like here the results are even worse than those in the book, but maybe that's because it like less iteration were done or something.
The parameter as
Yeah, okay, yeah, let it be. It's not really that important. Oh, so there are.
or there might be some other changes that needs to be done because I can see here from study this guy and I think so. It will take some time. In the meanwhile, Arto, you can take back the control and
Okay,
guide
okay.
us. Yeah.
Yeah, so I guess you can keep sharing a screen, or should I? Okay. Let's get back to the book. So here, yeah, we discussed this figure, and now here is an algorithm for n-step semi-gradient TD. And again, that's similar to the TD0, but it's a bit more complicated because we need to do this and step bootstrapping, but the idea is the same, right?
One question on this. I noticed like in all of the algorithms they get, it starts, you see like the second line there, like input differentiable function v hat. Where does v hat come from, do you know?
V hat?
Yes, so see the second line says that v hat, like that's the estimate of it, the state value, isn't it?
Okay, so
but yes, it says like
second line in
no, second line from the top where it says input.
Okay, a differentiable
input
function.
A differentiable function.
Yeah, so it's just okay. I get it.
Yep.
Yeah, so it's a function. So that's just a product of w and x. So x is a feature vector, and
oh right, it's just a linear function there, is it?
Yeah, and so weights would be our just like if you you can initialize it randomly, or here they say we initialize them equal to 0, right? So in case of linear function, we don't have this initialization problem as in neural networks. So we can just initialize everything, all weights to 0 and still converge. And the feature vector, actually we will be like talking how you can construct feature vectors in different ways here. So, and the function is just this.
All right, sorry, I hadn't realized it was just the one that came before at the top. I thought it came from somewhere else. I wasn't sure what it was. Okay, cheers.
Yeah, in general, it's just like simple concepts, but probably a lot of noise here. I don't know. So a lot of notation here, so that might get confusing at some point. Yeah.
This is a semi-gradient method, if I'm not mistaken, right?
Yeah. So the semi-gradient method, and yeah, again, all the bootstrapping methods would be semi-gradient because yeah. So the true.
So it's because of this, yeah.
Yeah.
Yeah, it just doesn't consider the gradient on the estimate, isn't it, when it's bootstrapping?
Yeah, so here in this line, you see that the approximation for the returns also depend on W, but we don't consider the gradient with respect to this, right? Yes.
I think so. It's with respect to this guy and this guy. Here we can consider the gradient here, but we do not consider it here. In the same statement, we do not consider it here. This is not there.
Oh, sorry. I just moved everything. Yeah, so when we were deriving this bit here, so it comes from the squared error, right? And when we were taking the gradient of square of a function, we were assuming that this component was independent of W, and that is not true for bootstrap, for any methods that do bootstrap, because the value of G depends on W actually. But yeah, so that is why we got to use semi-gradient method instead of true gradient method. And I believe they mentioned somewhere in the book, or maybe it was in the DeepMind lectures, that you can do like a true gradient for TD as well, but obviously that would be much more complicated. Yeah, the math would be complicated. I don't know how it will combine with auto differentiation software. So yeah, but that's really, I think also the convergence proof, for example, we had here, it assumes a semi-gradient method. And yeah, so that is kind of maybe and at next session, if you'd like, we can try to go into some details, but I am not sure if that would be relevant for us, because we are still talking about this linear function, so we are considering very simple cases, and those are mostly used to demonstrate some failure cases, but I guess to do this kind of analysis for more complex functions like neural network, we would require much more work, and I'm not even sure if it's done anywhere at all. So I think the deep RL is more empirical, and yeah, it has relations to math behind it, and all the like convergence proof and stuff like that. But I guess that is also kind of trying to converge to one place, but it hasn't yet, right?
Yep, true.
Okay, so let's now go to more details on how you can construct some features. So here, what we have is a state, and to compute this linear function or any function, basically we want to compute, we need to process the state in some way to make it compatible with the function we use. And here we consider different choices for feature extraction. So again, that would be, this will be kind of related to the classical machine learning a lot. And here, the first choice we consider is polynomial choice. So we will construct our feature vector as a vector of polynomials based on the state. So consider some state, so some environment where a state is described by two numbers, S1 and S2, which both are just rational numbers. And now we can construct our feature vector, x of s. So the simplest feature vector we can choose is just to stack these two numbers in a vector. But what we can do, we can add some combinations of states. So in polynomials they use here, we will consider the combinations of S1 and S2 up to some power, depending on the our choice of polynomial. So here we have for polynomial of degree 1, we have like 0 degree, which is 1, and degree 1, which is S1, S2, and product of S2 and S1. And notice here, then in this book, they use slightly different definition of polynomial features, I think, compared to the generally accepted one, where the polynomial of degree 1 will only consider interactions up to degree 1. You can see that this last term here is the second degree interaction, but here they kind of chose it to be for the polynomial of degree 1. But that just, you know, how you defined it. And here they defined it in this way. So the second degree polynomial for these two states would be, you see, it will include all the possible combinations of S1 and S2 with power of up to 2. Okay, and yeah, so here you can see that if we have a k-dimensional state vector, so k-dimensional state space, the order n polynomial features can be written as, so that would be kind of a way to write all possible features. And here C sub ij is an integer up to n, right? So that's just a way to write this down in this like a short form. And for n order n polynomial and k dimensional state space, we have n plus 1 to the power k features. Okay. And the question, why does 9.17, so here, why do we have n plus 1 to the k features? And the answer kind of comes from the combinatorics, right? So we have kind of we have n plus 1 numbers for a power, so it can be like 0 up to n including, right? And we can have a k choices for that for that power. I mean, so yeah, if you imagine, like you write down all the possible products of k states and all possible powers, you will see that you have kind of, you can think of it as a kind of a row of numbers having k choices for each entry, right? And where the number of entries would be a dimensionality of state space, or not dimensionality, but the degree of polynomial, and k would be the choice of so the number of choices would be a dimensionality of state space. So that's how it turns out to be, right? Yeah, and what and Cij produce the feature vector 1 up to, okay, so that's kind of obvious, I guess, that this is second degree polynomial. So I don't know what the question is about, actually. Right.
This,
So
I think so, is about dimensionality of the K, which is the natural state space.
yeah, I mean, in this question, it's kind of already obvious what the answer is, right?
Okay, okay, okay. Yep, yep, yep.
It just, I don't know, rather simple question, not one you are used to see in this book. So I was kind of surprised, but yeah. Okay, so the polynomial feature is choice is simple and well studied, but it's not always the best choice. So another popular alternative to it would be Fourier basis. And in this case, we can represent our feature vector as a bunch of cosine functions with different frequency, right? So here we consider, as you can see, this is not a full Fourier basis, but half interval. And in this case, we consider only cosines as a basis, right? And here I denotes a number of frequencies we take, right? So it here you can see like frequencies from 1 to 4, and in this case our state is in interval between 0 and 1, and the features would be values of the cosine evaluated at S, and it will be a combination of all these cosines with different frequency. So that is also relatively simple and kind of familiar way to represent a function. And here you can see that this what features it will produce when you extend it to the kind of two-dimensional case, right? So it will be just this kind of this is kind of a heat map here, and the dimensions are our values for state dimension 1 and 2, and here is a value for the Fourier basis function for this particular C here. And then we have another C and another C. You can see that when we select this cosine to like in two directions, then we have this kind of diagonal pattern here, and then we increase frequency, and we can also have different how it's called, like inclination of this stripes here. And yeah, actually the stripes here kind of represent the intensity, and you can imagine it as a 3D kind of wave, right? Representing the value for each of the possible S1 and S2. Okay, and then you obviously can easily extend it to higher dimensions, but you cannot easily visualize it, unfortunately. Yeah. Okay. And here is interesting thing to, note here that when using a Fourier features, the learning rate is usually said to be like dependent on this C values. So we kind of normalize it by the square root of sum of squares of all C sub i's. Okay. And in practice, it is claimed that the Fourier bases perform better compared to the polynomial basis. But these are results for the random walk example, the same we considered before. And yeah, that probably might be dependent on some properties of the environment, because like again, if we want to draw some like parallels with machine learning, this kind of feature engineering is an extensive field of study, and in some cases the features are kind of handcrafted to match the properties of underlying process we study. Or you can like, you know, that in machine learning it is often some pruning techniques are applied to select most useful features. So some feature selection can be done, and yeah, so we don't have to use all the combinations we can produce, but only the most useful ones. But I'm not sure how this all extends to the RL applications. So do you have your variant of these figures, Mayank?
Yep, I have a figure here, but it's not much different. Let me try to share it.
Yeah, I think if it's very similar, we can just skip
Yeah,
it.
yeah.
I was just curious if your results match this one, because I haven't yet implemented uh, like examples from this chapter, so I'm curious how did it work. Okay, so now we can move to the next way to encode the features. And this is another very popular approach, which is called coarse coding. And here you can imagine we have some 2D state space. And to encode the state space here, we will just randomly fill this area with overlapping circles, and say take some point here. Let's consider this S prime, right? So for S prime value, we will have this. So it is inside this circle and this another circle, and these two features. So we have like one hot encoding vector, or like not one hot encoded, but binary vector, and of size equal to the number of circles we have here. And for each location where we this which like encircles the state we are interested in, we will have one here in entry, and for all other circles we have a 0 entry. So once we have this, if we have a state space nicely covered with some number of circles, then we will have a meaningful representation for each of the possible states, and it will be like this binary vector representing each possible state. Okay, and you know that we can measure a similarity of states judging by this similarity of the vectors produced by coarse coding. Okay, and
Yep. In the lecture, I think so. Hasso gave a good representation of how coarse coding works with the Gaussian distances and the representation of the lines that had the number of circles. So,
so in the lecture by DeepMind.
yep, the
Okay, so
21
here
lecture.
I guess, right?
Yep, yep. I think so. You might have seen, but let me try to share my screen quickly.
Yeah, sure, you can share. Let me stop and.
So here is feature reconstruction example, the feature construction example that we worked. This is the Gaussian distances. We presented the sigma I is a distance. As you alluded to earlier, the number of circles are represented by the number of points that this has in this list. And those circles will be activated to have the shaded the color that is shaded other than white. So here they are taken for a particular point in this graph. They have taken 1, 2, 3, 4, 5 different circles. And then this is narrow, then the broad, and the asymmetric generalizations, which they talk about difference between them in the text too. That was it.
Yeah, the lecture on the function approximation, I think it was a really nice one. And yeah, they had some good explanations there for and some derivations, so that was useful. Okay, so and there is a bunch of hyperparameters you can choose when doing coarse coding. So for example, here you can see that depending on how much of overlap do we have across the circles, it kind of, we have a broader or more narrow generalization. So to rephrase it, it's kind of, you can see that more circles are likely to activate in this case than in this case. So when we have more overlap, we have a broader generalization. And if we have less overlap, so I think the number of circles here is supposed to be the same, but you can see that the circles are larger in this case, therefore they overlap more, and each state will have like more of these circles activated, and yeah, therefore that will result in broader generalization, because kind of closed states are more likely to have a similar representation than in this case. And yes, so here is an example of how like what kind of results different settings for coarse coding would produce. So we have target function here shown in blue, and it's just this rectangular function here, and we are trying to approximate it using different kind of feature widths. And so here you can see that with narrow features we will get this kind of bumpy approximation, and with a bit broader features we will have kind of less bumpy. And you can see that the final result is very similar for all feature choices, but the intermediate results we have here are much more different. And in case of broad features, we have this kind of smoother function. And in case of narrow feature, we have this more sharp.
Yeah.
Yeah, but the result in the end is similar, but yeah, that doesn't tell us much. Probably this choice also depend on what kind of like underlying structure you expect to have in your environment when you're using broader or narrower features. So if neighboring states are expected to be very similar, then you would like to use broader features. But if you want to allow kind of sharper jumps in state representation, then you would like narrower features. Okay, and an alternative to circles can be this tile coding. It's so the idea is very similar, right? We have this continuous 2D space, and we just instead of as we did here, we just used this random circles, but here we can produce a bunch of overlapping tiles, and we can do it deterministically and still get good features from that. So here you can see a point in a continuous 2D space. And here you can see how it will be represented. So yeah, so for each kind of the styles, we will have an entry in our feature representation. And yeah, here you can see that, yeah, so here we have like 4 tiles, and yeah, what are they computing here? Why it's 3 4s? Yeah, let's just, yeah, so here in this figure, the state aggregation can be considered as one using one tile, right? So we do not have any overlap between tiles. If like in that figure, we saw before for that random process, we had a state aggregation, and that can be viewed as like particular case of tiling when you have only one tile, like you don't have any overlap over tiles. But here you can see that when you introduce 50 tilings, then it will be, so that produces much better results here. You can see that here the error stop improving because the expressivity of our function is kind of limited, but in this case the limit is further, so it can produce. I wonder if they have kind of this. No, I guess not. Okay, and here you can see that we can have different choices for this, how we arrange the tiles. So we can do the like symmetric, we can use symmetric pattern or asymmetric ones, as done here. And yeah, probably that, yeah. Let's see. Yeah, so here they state that when you use asymmetric tiling, the generalization is more homogeneous, and as compared to the symmetric one. Yeah, and you can have different choices of offsets and different choices of patterns here. So, for example, they use that the tilings does not need to be grids, but they can be kind of arbitrary shapes, and you can use some kind of irregular shapes for your tiles, or you can use this logarithmic scale, logarithmically scale stripes, or you can use diagonal stripes instead of kind of this to go in aligned with the axis. So yeah, so there are a lot of choices. And yeah, so another thing you can do, instead of using the styles directly, you can use some hashing function, and in this case you will kind of collapse tiles into one tile using some hashing function. But yeah, so as I don't go into much of details here about that. Okay, and finally we get to the radial basis functions. So instead of using this binary features, we can use the continuous features. And one popular choice for this is radial basis function. So we have this bell-shaped regions, which are determined by the mean and a variance, if you think of it as a Gaussian, right? And we will encode each feature as a combination of this radial basis function. And you know that this is one of the most popular choices for SVMs, support vector machines, where you use a kernel trick, and radial basis function is one of the most popular choice for the kernel function there, and it works very well. It gives smooth, like a nice expressive kernel for your features, and the same kind of function can be used here to produce a feature representation of a state. All right. And there are a bunch of references where you can where you can refer for details on the use of radial basis functions for function approximation in reinforcement feature representation and reinforcement learning. Okay, so with that, I think we are done with the choices, most popular choices for feature extractions. And another important topic when doing optimization, we have this step size parameter, so our learning rate. And for all this algorithms to work well, we need to set the step size appropriately. So here we have some recommendations of how you can select a step size. So for Monte Carlo methods, we usually set learning rate to be decaying with time as the reciprocal of time, right? So 1/t would be our step size. And yeah, so for the linear case, there is a least squares temporal difference method, and it's described further in this chapter, and it can be yeah, so it is more computationally expensive compared to the methods we considered before, but here they so here you can kind of relate it to the, so yeah, they give us this rule of thumb to choose a learning rate for SGD depending on your features, and the tau were kind of how many experiences do do you want to have with the same feature vector, and yeah, that it can be given as this number, but yeah, that probably doesn't make too much sense for you before you try to use it, I guess. So
Let's
and
keep it up until here. Till equation 9.19. We can start the next.
okay, cool.
Yeah.
Yeah, I think that the common parts here are very high level. So we have some information about applications of neural network for reinforcement learning, but it's kind of very high level overview of what you can do. And the same about least squares TD. So they give here. So yeah, but okay, let's postpone this to the next session. I just wanted to say that all these sections are just like very high level overview of some concepts, right?
Yep. Truly.
Okay.
Yep. Yeah, this chapter here, this chapter has been like a huge chapter. If you look at like how many pages, it's what, 40 pages, whereas like the next chapter is only 12, I think. So yeah, you did well getting through all of that.
Yeah, and I think they sometimes kind of there are some jumps in what are they talking about, which are like, yeah, I think because authors try to cover a lot in one chapter, so they are trying to introduce us to like a lot of information about function approximation here, and so therefore they have to like jump from neural networks, and you can see here some convolutional network, right? And
Yeah.
then we are here at least squares temporal difference method, which assumes, I guess, some knowledge of linear algebra, and yeah, so, and I guess
Yeah, like I didn't understand a lot of it until I went and watched the DeepMind thing. Like, well, with him going through it again, he sort of maybe doesn't go into as much technical detail in it, which was better, I think.
yeah, the DeepMind lectures are pretty nice complementary for this book, I guess. But
Yep.
also the lecture 7 in the lecture series, I think they say it corresponds to chapter 9, 10, and 11 in the book. So it's also quite bunch of information
Yeah.
here.
Yeah, I've only watched half of it so far, so yeah.
Yeah. Okay, great. Thank you for attention, and yeah, feel free to communicate anything on the Slack if you have something during the week, and see you next Sunday, I guess.
Yep. Thanks very much for that. Cheers. Catch you
Sounds
next
good.
week.
Okay, bye everyone.
Cheers. Bye.